Let's go on that. So we're going to start off with integer addition. And so we need two things here. We need a model for integers and we need a model for addition. And we were playing with those chips yesterday. So for me, I'm going to draw them. And my shaded one is going to be like your red one. And that's a positive. And the open one is going to be like your yellow. Are yours yellow or white? Yellow and red, is that right?
Yellow.
Yellow, okay. Some sets are yellow and white, or red and white. So yellow is going to be a negative 1. And the other catch about the integers is we have two ways to show 0. 0 could be nothing, or 0 could be the combination of a red and a yellow together. So that is another way to show 0. So from now on, when we work with integers, we're going to have a key for what our model is. And our model could be the chips, because the chips are convenient, and they're in a lot of classes these days. But it could also be you have a set of pluses and minuses, which are really nice to work with and easier to draw on the board. So that's nice too. So we're going to have some kind of key. So there's my key. Next, what does addition mean?
Combining.
Yeah, it means the same thing it did before. Addition means combine and count. So we're just going to go over modeling a few different problems, and then we're going to try and take those modeled problems and turn it into an algorithm, because we don't always want to have to whip out these chips to solve an addition or subtraction problem. So let's say, could you, with your toys, illustrate -4 plus -3? What does that look like with the toys? So illustration-wise, it's going to look something like this. I start off with a set of -4 and a set of -3. I need to combine them and then count and see what I have. So pretty straightforward. It's -7. Looks a lot like 4 plus 3, right? Okay, so no big deal there. So similarly, if we did do 4 plus 3 with these toys, it would look pretty darn similar, except I would have a different colored chip. So I would have 4 red chips, or shaded chips for me, and then a set of 3 shaded or red chips. And then we combine and count those. And I like groups of 5 whenever possible. And so in this case, I get +7. Pretty straightforward. Let's try another pair of problems. How about if we try 7 plus -5? We want to use these toys and our key to figure out what that sum is. So I have to make myself a group of 7. I'm going to make myself a group of 5. And then put them together. So this is my new set, but what's the catch about this new set?
You can combine them and make some 0.
Yeah, I can make some zeros here. Oops, I forgot to shade a couple. Yeah, there's a bunch of zeros sitting here. 1, 2, 3, 4, 5 can be recombined to be 0. So what's left over? So the answer here, after I combine and count, it appears to be just 2. Does this look like another problem we've done before? Maybe not the model, but the different problem with an answer. What can I say this is similar to? Comparison model for subtraction? Isn't it like I compared 7 and 5 and I found they're 2 apart? Right? Here's my 5 there compared to a set of 7. Here's where they match up. Here's where they're different. So this looks a lot like 7 minus 5 is 2. Okay? Just a note. That's what the comparison model for 7 minus 5 would be like. Okay. All right, let's try another one. How about 4 plus -6? You could draw it or use the toys. So we start putting them together. And in this new set, we can note, hey, I can make some zeros, because that's a fun way to play with our toys. And we have left over, careful, -2, yeah, those are like my yellows. So there's a -2 left over after I combine and count. Okay? And part of the counting here is counting up when zeros happen. Now, this sort of looks like a comparison, doesn't it? Comparing 4 to 6, and they're 2 apart. So it kind of looks like if we're working with whole numbers, 6 minus 4 is 2. But instead, what we have is slightly different. We have that 4 minus 6 is -2. So it seems like sometimes with integers, when we combine them, it's like a subtraction problem, like this one right here, and this one right here. But otherwise, there's other times where it's just a straight addition problem. So can we tell ahead of time when an integer addition is going to be a straight addition and when it's going to be more like a subtraction? What do these two examples have in common? What does this and this one have in common? So let me summarize those. We had, let's see, what's the first one again? 4 and 3. So -4 plus -3 was very similar to 4 plus 3. And then we had 7 plus -5. And I think that was kind of like, what was it, 4 plus -6? These involve the straight addition. These were very much like subtraction, okay? So what are the characteristics that the first pair has, and what are the characteristics the second pair has? So we can identify a rule. What's up?
The parentheses around all of them, why don't we do that stuff first? Or is that what we're doing?
Well, there's nothing to do inside the parentheses, so that's a different situation. We put the parentheses around negative numbers because otherwise it looks kind of weird. -4 plus -3. What's that, right? So here we put the parentheses to indicate that's not a minus, it's a negative sign.
But can't you switch the subtraction sign into a positive sign and make that 3 positive?
That's a whole nother rule we'll get to in a minute. Yeah, so you're a little ahead there, that's cool. Any other ideas, Monica? What do you think?
So in the straight addition, both of the numbers are positive, or they are both negative?
They had the same sign. Yeah, that's definitely important. This grouping right here, numbers have the same sign. Okay, so once we identify that here, what can we say about the other pairs? They have different signs, yeah.
Different.
Because what we want to do is we don't want to have to whip out the toys every time we want to do this or start counting on a number line, right? Because what if the numbers are bigger? So what I'm getting to is how would I tell somebody how to do something like negative 125 plus 78? How do I describe what to do? I don't want to whip out chips for that. I don't want to do that on a number line. I just want to say, hey, follow these rules. Okay? So this fits in the different sign category, that problem I just put up there. Okay? So what did we do? What did we relate those to? Well, in this one right here, it pretty much turned into a straight subtraction problem. And in this one right here, it turned into a subtraction problem, but I had to think a little harder about what the answer was. Okay. So what I'd like you to do is take a minute and write down the rules that you would tell someone to follow if they ended up with a problem that looks like that, or maybe the problem looks like this one. What rules would you tell someone to do to get an answer there? So why don't you do both of those and then think about the rules you use to get the answer. So without a calculator, how do you compute those sums? What rules are you following to make that happen? So there's a common set of rules for those problems. Give it a shot, write something down. So there's my work for the first one. Yours might look something like that. And there's my work for the second one. So these are alike but different. Which was easier, the first one or the second one?
Second one for me.
Second one was easier for me for a couple of reasons. One, the subtraction happened based on the sign the 142 had. But on the first one, I had to subtract in a different order than it stated. We don't usually do things that look like this, do we? Has anyone ever written that down before? I don't think maybe I wrote it down once in my life to be difficult, but we usually don't write things like that. This makes more sense, right, compared to what we're used to? Yeah. So one thing has to happen in this step. There's got to be a subtraction that happens, but then I have to figure out, is the answer positive or negative? Okay.
Can't you figure that out by the numbers? The bigger number, like on the first one, is 125, so it's a negative, so it carries.
So what do you mean by bigger? I thought 78 was bigger, because it's further to the right on the number line? You have the right idea, I'm just picking on your language.
Like my flower?
I think maybe because it's farther away
From?
from 0?
Yeah, that's the key, yeah. The further from 0 it is, that's what you meant by bigger when you said that.
Yeah.
But technically, bigger means greater, and greater means further to the right on the number line, right? So the language is important. So essentially what you did is you kind of thought about the absolute value of each number. That's an important idea here, right? So one, I gotta consider the absolute value of each number. What's absolute value mean again?
Distance from 0 on the number line.
Yeah, and so with kids, we're gonna use the word absolute value, but mostly I'm gonna talk in plain language. I'd rather say, consider their distance from 0. Okay. Which is the absolute value? Distance from 0. Okay. So I need to consider that. Once I've done that, then basically what I want to do is I want to take the smaller absolute value away from the larger absolute value. So then I can do what looks like a regular subtraction. I'm just going to shrink this a little tiny bit. And then there is a third step. And the third step is determine the sign of the answer. That's going to be the sign of the number that was further from 0. So answer gets the sign of the number furthest from 0. Number with the biggest absolute value. And that's pretty much the steps we follow. Now, we might not think of it in that much detail, but how many people did this subtraction on their paper right there? Right? Didn't we all have to do that? Yeah. Did anyone do that subtraction right there? No, we don't do it that way. Right? Could we? Yeah, but it's weird. Right? So we stick back to what we know, and we know how to do that. And then I had to say, well, the answer's not really positive. The answer ought to be negative because that one's further from 0. That's our decision-making process. Does that make sense into how you determine your answer? Okay. The way you word it might be different, but those are the rules. Okay. So that's what we do if the signs are different when we're adding. What if the signs are the same? So if the signs are the same, like maybe negative 125 plus negative 87, for example, how do you do that right there? What's the process you would take to make that happen?
I'd still put the 125 on top.
You'd write 125, and underneath you'd write 87, right? But they're the same sign, so you're going to add them, right? So 5 and 7 is 12, 8 and 2 is 10, plus 1 is 11, 1 and 1 is 2. So the answer looks like 212, but
Negative.
it's got to be negative because the numbers were negative. Yeah. So what happens here is absolute value is still involved, but the answer, you just add their absolute values, and the answer gets the same sign. So 1, add absolute values, 2, answer get sign, there we go, of the original numbers. So I have to make a decision. When I'm adding, are they the same sign or are they different? If they're the same sign, add, pick the right sign. If they're different, you have to subtract. It's a little trickier. Question?
But I thought if you had the bars
Yeah.
for absolute value, the negative 212 would still be a positive 212. Because it's the absolute value.
So what's the, so again, there's 2 steps here. The first step is to do that. So what's the absolute value of negative 125? Right, and that's what I wrote right here. What's the absolute value of 87?
87.
And that's what I wrote here.
Okay.
So I added their absolute values.
Okay,
But then I have to go adjust the sign.
okay,
Right, so that's the second step. So addition of integers is a two-step process. If they're the same sign, it's a three-step process if they're a different sign. But it's a decision-making process. It's pretty complicated. Okay? Does intuition of playing with these toys help? It does definitely help. Okay. Thinking about gain and loss helps, especially with these right here. This is a loss of 125 and a gain of 78. In terms of gain or loss, what should happen in the end here? It should be a loss overall, right? Which means a negative answer. So there's a couple ways to think about that. All right. So that's addition. We played with it a little bit last time in terms of models. Now we have an algorithm. The algorithm is a whole bunch of steps. Okay? A decision, and then we have to go with which set of steps based on that. Let's play with subtraction. So, we need both of those. There's an extra. We're going to play with subtracting. We did a couple of these in class last time. We'll review quick, and then I'm just going to set you guys to play with these on your own for a little bit. So these are two different worksheets. The first one is that this one right here?
yeah.
Yeah, we played with this in class the other day, so I'm just going to go over a similar example for this one right here. So there's a couple of cases that happen when you're subtracting integers. And some observations we have to make. So in order to come up with our routine, our algorithm for addition, we had to make a whole bunch of observations. Same thing's going to apply here. We have some observations to make. So consider the problem of 3 minus 4. 3 and 4 are both integers. Okay? Let's use the takeaway model. So things to consider here. Subtract means takeaway. The other thing is we have a key that's important, that a red or solid is a positive one, a yellow or open is a negative one, and then when I put two of those together, I get a 0. So I need to know what an integer is for modeling, I need to know what subtraction means for modeling. Okay. So the way the takeaway model works is, in this case, I'm going to start with 3, and I'm going to try to take away 4. Okay, let's see. So here's a set of 1, 2, 3, and they are positive, so they're shaded or red. I can't take away 4. Darn it, what was the trick we applied Monday?
Add 0.
Add 0.
Add some zeros. Yeah, so I'm just going to go in here and I'm going to say, well, the net charge of this set is still 3, but now I can take away 4. So I just had to add enough zeros so that I can proceed with whatever I needed to take away. Here, 1 0 did it. Sometimes you might have to add more than 1 0. Okay, so now, take away positive 4. Looks like that leaves what? Just a negative 1? So, does this picture look like something we drew earlier? What does it look like? Picture of what? What other math problem would look like that when I circled?
Partition. Is it partition?
No, not partition, not a different subtraction model. We just did addition of integers, right? Does this look like a picture of an addition problem?
Yeah, the first one we did where it's similar to the subtraction one.
So what addition problem would this be right here?
4.
This would be 4, right? Let's see. -4 plus 3. So it doesn't really look like that, does it? But does 3 plus -4 give us the same answer? The rule for this one right here would be to do the subtraction 4 minus 3.
Yeah.
And then get the sign of the number furthest from 0, so we get a -1 out of that. So they're similar. Okay, so what you need to do is turn the page. Actually, let's see. There's one to do on page 1, -2 minus 5. And then there's a few to do on the next page, problem number 2. So what you want to do is play with your toys and draw some pictures related to each of these. And we're going to try and come up with some rules. So I'm going to let you guys walk through those. I would recommend getting a partner or partners to work with. And then we'll come back and group up and check it out.